pleasure to introduce Diogo Bolster. I've been practicing that name. Fabio's been telling me how to pronounce it, and finally he gave me the right recipe last night. Diogo comes from the Department of Civil, Environmental Engineering and Earth Sciences, so it's not too dissimilar to ours. I suppose they just replaced the word geo with Earth Sciences at the University of Notre Dame. I always said Notre Dame, but it's wrong. Diogo has a very interesting background. He was the son of a diplomat, so when he was young, and up to when he was 18 plus, he traveled all over the world. So it's almost any country you can imagine that he's been to. So it's very interesting to talk to, and he knows lots of things about different cultures. And I think that bleeds out very much into his research, because again, if you look at his research background, he has actually been in various appointments as postdocs and students. He's been in physics departments, mechanical engineering departments, civil departments, and environmental engineering departments. So he has a very wide range and spectrum of things that he does. And as a result, what I like most about his research is very eclectic and open-ended kind of ways to solving problems. And he's going to address some of that today in his talk, which is going to be on incomplete mixing in reactive systems, particularly a reference to porous media. Diogo, it's all yours.
Well, thank you for that introduction, which is more elaborate than any introduction I've had. I appreciate it. And thanks for inviting me to be here. Thank you all for being here. So before I get going today, I want to thank my collaborators. I think most people like to put up a list of collaborator names. I prefer putting up photographs because you might bump into one of them someday, and a name doesn't mean much. But without these guys, I couldn't have done any of what I'm about to present today. So I'm grateful for that. To give you a bit of background on the kind of things I'm interested in and the kind of things that motivate the work I'm doing, for any of the graduate students, well, even the professors here, if you go back to your undergraduate times, even some advanced graduate courses that you might have taken, contaminant transport is often treated like this, right? We think about the world as homogeneous. The equations, they don't reflect the real world in any way, shape, or form. Whereas you go to the real world is complex. And then we use this word heterogeneous. And I mean, heterogeneous, the only thing that means is not homogeneous, right? It doesn't tell you anything about the specific structure or complexity that exists in there. And so this is, Degan is famous. He's the godfather of the field of stochastic groundwater hydrology. And the cover of his book tries to convey this by sketching these four different depictions of heterogeneous porous formations that exist. My very first PhD student at Notre Dame was a geologist, and he got furious at me for putting this up as an example. He said, why would you do that when you could do this? Right? I mean, the point is you don't have to go very far in the real world to recognize that heterogeneity is ubiquitous. There is no such thing as a homogeneous system when you're talking about Earth systems, right? And really that's kind of what I've been trying to embrace. At the same time, this is what I teach in my undergraduate courses on reactive transport. I still teach them the homogeneous world perspectives. And so this is the kind of thing that you'd often envisage or see. Imagine you have some sort of reservoir that's filled with whatever that blue substance is. I don't really care. And then I continuously inject the red substance from the left-hand boundary there. You expect kind of a nice homogeneous space with a dispersive transition region, right? So everything is nice, smooth, clean. Described by an error function if you're interested in the mathematics or the likes, right? And then you go down here, and here we have again a uniform flow going this direction from left to right. I put a point injection. That point injection advects downstream and at the same time is dispersing or diffusing. So the concentration you can see is high. Everything is circularly symmetric. It's decreasing over time. And if I take a transect, if I cut through this, I get a nice Gaussian profile. Right, so this is absolute standard textbook. You go into the real world, and things start to look like this, right? So in the real world, you have an injection in a well. You don't see things going out in a nice circle as you expect. You see things that are reflecting the inherent underlying geologic complexity that's there. Here again, this is an experiment where you have a flow taking place in this rock formation, and you can see there's a preferential flow path that's moving up that left-hand side. Laboratory experiments. Things don't look anything. I mean, there's some resemblance to those theoretical solutions that we talked about before, but really things start behaving quite differently. Another thing, so breakthrough curves are things that we often measure, whether we're working in streams, in aquifers, or many hydrologic settings, right? You have some sort of flow, again, unidirectional flow. You inject a pulse or it can be continuous as well, but you inject a pulse in a given location, and at some downstream location, you measure the concentration as it passes that point, and you get a breakthrough curve, right? So you have concentration against time, it rises, and again, this is, if you believe what's said in textbooks, this will be described by a typical solution to the advection diffusion equation, which is a Gaussian in space. You go into the real world and conduct these kind of experiments, and you see features like this, right? So textbook will tell you concentration against time. You expect this solid, smooth line, and instead people observe things like double peaks, right? So which is suggesting that there's actually two pathways in the subsurface that you're somehow not accounting for. Or really the thing that I'm more interested in, right? Here you have log concentration against log time, and it's focusing on the trailing edge of the breakthrough curve, so the tail. And theory would tell you that you have this exponential cutoff, so something that starts decreasing very, very, very quickly. And time again, in real environmental systems, you tend to see this persistence and power law tailing, right? And so many people kind of say, well, power law tails, they happen at low concentrations. They're not really that important. But I want to point something out. If you take this guy out to here, right? So extrapolate this on, and it persists this way, you will end up with a mismatch in what your predicted concentration is, right? And what your measured concentration is that is off by 50 to 100 orders of magnitude. Not a factor of 50 or 100, 50 to 100 orders of magnitude, right? I mean, that's mind-boggling. So depending on the kind of thing you're interested in, these power law tails are actually really, really important, okay? And then finally, for the case of introduction, what does homogeneous even mean, right? So this is an experiment that was conducted in Israel, and this is a clean sand. I mean, is probably the most homogeneous thing a geologist could envisage, right? And they have this tank packed, and what they have is, again, flow from left to right. They put in, I think it's 8-point injections, and you can see that they evolve as they go down. I mean, it doesn't look terrible, right? But clearly those don't look like the nice Gaussian distributions that we were talking about before, and each of these injection points looks a little bit different, right? That's reflecting the fact that within a porous medium, right, you can always zoom in, and if you zoom in, there is always some small scale where there is a heterogeneity, right? So within the pore scale structures, things aren't completely homogeneous and even, right? And that's reflecting itself in this large-scale behavior, okay? So what, right? How do we cope with this? Well, if you go, I mean, I don't know how many of you are familiar with anomalous transport literature or people who work in anomalous transport. If you ever want to see academics fighting with each other, I highly encourage you to go to an anomalous transport session at AGU. I mean, it is unbelievable how the guys who represent continuous time random walk will fight against the guys who represent the fractional advection dispersion equations and the likes. It's really entertaining. But I don't fall into that camp. I actually think that all of these models are pretty spectacular, and they all do equivalent things. It really depends on what your perspective is or the problem that you're interested in solving. And they work really well, right? So I mean, they've had great success. They have their shortcomings, and people, are critical of many aspects of them in terms of applicability to, how do you actually apply them in a forward sense in the real world? But still, I mean, they seem to be able to capture these phenomena that we're interested in. But really, the problem from my perspective, right? So I'm going to be talking to you guys about things like mixing and reactions. The problem from my perspective is what these models do is they capture spreading, not mixing. And I'll explain to you what I mean by that. So this is an experiment that was conducted by a PhD student in Barcelona when I was a postdoc there. And you have, again, same setup as we were talking about before. You have a coarse sand with some fine sand inclusions, flow going from left to right. You have this red dye injected in there. And then this here, this is an imaged concentration field, right? So this is the exact same field here, but just translated into concentrations. And you can see, right, you have a spreading scale. So by virtue of the fact that you have fast flow through these coarse sands, you have fingers that go through, whereas these fine sands hold things back further, and so you have spreading. And so this is what I mean by the spreading scale. The total extent of your plume is characterized by that spreading scale. And if you're interested, right, so if you're interested in groundwater flow and water quality at a well, you don't really care about the fine scale structure of this. You want to know how fast is my fastest point moving and how slow is my slowest point moving, right? So imagine I'm trying to capture everything at a well here. But if you want to know how this water is interacting with this water, that spreading scale provides you with very, very limited information. Because really, the only place where interactions are taking place between those two waters are these green spots here on this image here, right? And so that's what I mean by the scale of mixing. So you have small scale mixing and large scale spreading, right? And right now, all these models that we have cannot capture mixing dynamics. They seem to be capturing these kind of spreading dynamics really, really well. Okay, for any of you who saw the title of my talk and thought you'd see some chemistry, I apologize to you up front. I'm not a chemist. For me, chemical reactions means A plus B goes to C, right? And that's about as complicated as I'm going to get. If you believe the physicists who study chemistry, they argue that understanding this means you can understand anything. But I'm not going to defend that point today, right? But really, this is what I'm going to focus on, right? And I'm going to take you back, again, for some of you in this room, maybe it's not that far away. For me, it goes back to, I remember doing this exact type of experiment in secondary school back home in Ireland. And it goes along these lines, right? You take equal amounts of some reactant A, reactant B, and they produce reactant C. And you measure how quickly A is being consumed or how quickly C is being produced, right? And if you do the experiment carefully and really include equal amounts of the two, you should observe a behavior like this, so that the concentration of your reactants, right, would decrease. So it follows this solution here. But at late times, it will fall off as a power law like t to the minus 1. Okay? And that's really what I want you guys to focus on. Don't worry about where this comes from or what's going on. Just really, at late times, it falls off at t to the minus 1. And again, any of you who did Chemistry 101 as an undergraduate, you probably did this experiment. You measure, you get this data, and you can calculate reaction rates from it, or the likes. I actually went back, back home in Ireland. I keep telling people that I'm sure you did this in high school or university. I went back home to Ireland and I found my notebook. I did actually do this, so I'm not lying. Right? But anyway, a few years back, I'm still a postdoc in Barcelona, and my postdoc advisor says, let's study this, right? I mean, and this very, very seemingly simple reaction. He said, but let's study this, but let's figure out how to do it in a new way. And he wanted me to develop particle tracking methods to study these types of chemical reactions, right? So random walk methods for any of you that know this. And at the same time, there was another person, he was a PhD student in a group that we collaborated closely with, who was going to study it using something called the Gillespie algorithm, right? And so we decided that we were going to take these particle tracking methods that kind of were in their infancy, and Dave Benson at Colorado School of Mines, if any of you know him, was kind of trying to push forward these ideas. And I'll run you through how this works, right? So these are particles, right? And they represent, each particle represents species A or species B. These things move around by diffusion. So by random walks, they can interact with one another, they can react, right? The first thing I want to make very, very clear is this is not molecular dynamics, right? I'm representing a concentration field, so I'm already working at a large continuum scale, right? But it's a representation. These are not molecules. This is essentially a way that you can discretize a concentration field into little particles and do this. And I'll run you through this algorithm really, really quickly so you have a sense of it. This was a large part of the work that I did here, right? So imagine, so this is a subsample of these particles. I have 3 of these blue particles. I have 3 of these red particles, right? And what I do is I say they're going to take a random jump. And the size of that random jump depends on the diffusion coefficient involved and the likes. And this is kind of classic particle tracking. So to take a jump, you can see this guy jumped here, this guy jumped here, and so on and so forth. Then within each time step, I do the following, right? So I have my particles there. What I do is I calculate the distance between the particles, right? So I take this red particle here, and I calculate the distance to each of its blue neighbors, right? And then you can show, using some pretty simple arguments, that if I want to know what's the probability that this particle here and this particle here react with one another, right, it depends on 2 things. The first thing is, what's the probability that those particles are actually going to collocate, right, so that they're actually going to come into contact with one another? And then, what's the probability that, given that they collocate, they actually react, right? So really, the nice thing about this algorithm is, this is entirely transport, right? So that has nothing to do with reaction. This is entirely reaction. Right? So if you have a very, very fast chemical reaction, things that come into contact are very likely to react. If you have a very slow reaction, they're not. Okay? And again, don't worry about these mathematical details. Anybody who's interested in that, I can run this through this. But the point is, now knowing the distance between these 2 particles and something about the chemical reaction, the rate of the chemical reaction I'm interested in, what I can do is I can calculate the probability of reaction between these two guys. I can then generate a random number, compare those two, and under certain conditions, a reaction takes place. Under others, it does not, right? So let's pretend in this case here the reaction does not take place. Well, then I move on to my next particle pair, right? So I compare these two. I calculate the probability of reaction. I generate a random number. If that random number causes the reaction to occur, I would get rid of both particles. If not, I move on to my next particle pair. So these two here go through that cycle. Now let's assume that the reaction does take place. And if the reaction does take place, what I do is I remove those two particles from my system. Okay? Now, one thing I want to make clear, I am not, so right now I am not tracking the product. So when two particles disappear, I remove them from the system. In principle, I could create a new particle that represents the product. I'm not doing that just because I'm really interested in studying the kinetics of what's taking place. We have other examples where we have done that, right? And I cycle forth and do this. I do this for every particle pair that can exist in my system. Okay, and we do this using some efficient search algorithms and the like, so it's actually pretty quick, numerically speaking. And then after I've checked for possible reactions between each particle pair, I move on to my step where I move them again by diffusion, and so on and so forth, to whatever amount of time that you want.
Do you change those probabilities as the concentration of the product increase?
Pardon me?
If you have more and more of a product that gets in the way of interaction, do you change the probability?
So no. So these are dilute systems. So there can be no blocking of particles if that's what you're talking about. We do not account for that in this particular case. So you can account for that, and we have done this within these discrete Gillespie algorithm approaches. But in what I'm showing you today, no, we have not considered anything like that. But thank you for your question. By the way, please, I don't know what the culture here is, but feel free to interrupt me as much as you like. I would prefer that, actually, right? But the point is that the PhD student who, meanwhile, he was in France, he was running this discrete Gillespie algorithm, which is fundamentally different from the algorithm that I just described to you, right? I'm not going to run you through the details of this. Any of you who are familiar with discrete Gillespie, wonderful. If you're not familiar with it, don't worry. It's kind of complicated to explain, and I don't want to get bogged down in those details. The main thing I want to point out is that the two of us were working with completely separate methods, right? And we produced similar results. So here, before I go on to tell you what those results are, I'd like to show you a simulation. So this is a two-dimensional simulation. So you can pretend this is that beaker that I was talking about before, right? And I have it filled completely with red particles, and it's completely filled with green particles too, right? You can't see the green particles right now because they're just plotted underneath the red particles, right? But you'll see in a second when I start playing this video, if you look at the edges, you'll actually see particles hopping around, right? And I just want you to look and observe and see what happens here. So my video is going, and again, like I said, you can see some noise here on the edges. When particles react, they're removed from the system. So now you can see, I wasn't lying to you, there are green particles in there. And this is how the concentration field evolves, or the particle locations evolve. Okay, I'll play that video for you again in a little bit, but before I do that, I want to show you some results. So this plot here, right, this is concentration. So this is the average concentration in my domain against time, okay? And if you remember, I told you guys that the theoretical solution said if I put in equal amounts of A and equal amounts of B, at late times, the average concentration in my system has to evolve like t to the minus 1. So like this light blue line here, okay? Now, Pietro and I were running our numerical simulations, we're doing our stuff, and what we observed time and time and time again, no matter how much we tried to avoid this, we would observe something that at early times matches our solution really, really, really well, and then at late times diverges. It pulls off, right? And this was months and months of work. One of us was a PhD student, one of us was a postdoc. As any of you who've been, who are currently PhD students, you go to your advisor with something like this and they tell you this is a useless numerical method, you've wasted your life, right? Brings tears to your eyes, it's difficult to deal with, but at first it was frustrating, right? You're sitting there going, what is going on? Like, what's happening? So we start looking closer and closer at what's going on, and we see, right, so if we change certain aspects, we can get better behavior for later times, but it always pulls off. But if you look at this late time behavior, right, so the way it pulls off, what we noticed is it always pulls off and transitions to another power law, right? So it doesn't just transition to something random. And so the question then is this transition to this other power law, is that a real physical effect, or is that some numerical artifact that's taking place? And so we dug into this a little bit. A crossover, yes. Pardon me. I'm not a physicist, and I don't mean to offend physicists. So we really started digging in the literature, and quickly we found actually that this is one of those typical things that people in different fields keep discovering over and over again. Including in the last year or two, I've seen some people rediscover this in certain areas. And you look and you see, the first papers I can find that talk about this behavior relate to astrophysicists, or astrophysics and early formations of the universe, right? But you can see particle physics, biochemical processes, turbulent environmental flow, population dynamics. This was one of the funny isn't the right word, but most interesting ones that I saw was a Department of Defense report where they were modeling combat on a field using these kind of methods, where the reaction was 2 enemy combatants come into and only 1 survives, right? But using very, very similar scheme. Why certain animals have spots. It's quite amazing, and really it comes down to the kind of phenomenon that I'm going to talk about today. So it's a topic that has a rich history. And I want to give you a perspective on what's happening. It's this, right? So this here, right? So you can see these are number of particles against space. So this is now a one-dimensional concentration field. And you can take number of particles, and that literally means basically concentration. So the dashed black line there, that represents the average concentration in your system. Blue is the concentration of blue particles, red is the concentration of red particles, and you can see that you have fluctuations and noise about the mean, right? And that's part of what happens. Anytime you use particle-based numerical methods, you're going to have fluctuations and noise about the mean. But any of you who've ever done an experiment, I mean a real experiment, not a numerical experiment, right, will know that concentrations are fluctuating, and there's these kind of things. Noise is inherent in all real systems. And so at early times, what you see is that the average concentration is significantly larger than the fluctuations, right? So to put this in context before I go on as well, what I mean by early are the times when my numerical simulations and that analytical solution match really, really well, right? Late times is when I pull off to that other power law behavior, and intermediate is kind of the crossover between those two, right? So at early times, right, my mean is very large, so the noise is relatively small, so therefore the mean is a pretty good representation of what's taking place. As I get to these intermediate times, now you can see that I have an average concentration, and the fluctuations are comparable in size to that average, right? So now the average is questionable. But more importantly, right, and this is something that's really important, there is no such thing as a negative concentration, right? Which means that now I get to a point where the fluctuations now dominate in the positive direction relative to the negative one, and eventually you have the average concentration. The fluctuations are much larger, right, than my average concentration. But not only that, I actually have regions. So if you look here, I have regions here which only have blue, and regions next to it that only have red, right? And we call those islands. And really, this is really important, because now I have regions where red and blue don't coexist, so the only way they can react with one another is by diffusing, okay? So they diffuse into one another, and that's the only way a reaction can happen. And so you enter into a system where everything is diffusion limited. It's no longer reaction limited. Okay, so now you jump forward. This is the exact same video that I showed you before, except, right, now you can see I have concentration against time. See this little box up here? This is going to tick forward in time, so you know where we are. This blue line, this is what the analytical solution that textbooks will have, right? This red line here, this is the concentration that we measure in our simulation, and the yellow line is an analytical solution that we developed. I won't get bogged down in those details. The only thing to point out is that this yellow solution and red solution seem to match quite well. Okay, so we take this, hop forward, and what I want you guys to pay attention to or ask is, what happens when these solutions start to diverge? So the blue and the red are starting to diverge. what happens? It's the first time you can actually see that there's green available, right? So let me play that again just to make sure. Up until this point, you hopefully believed me that there were green particles in there, right? But it was based on faith. You couldn't see them, right? But now they start to diverge, and you can see these green patches taking place. So really, again, this is exactly that same effect, right? You're now starting to see isolated patches of green, isolated patches of red, and the only way they can react is by diffusing into one another. And that's when this classical blue solution no longer works, okay? So our argument is that the numerical method that we've developed, right, is not well suited towards capturing well-mixed systems, right? But it is very good at capturing noisy systems where incomplete mixing effects happen, right? And for example, if you did this exact same thing using finite elements, finite differences, or finite volumes, you would not expect this divergence to occur, okay? Now, our argument here is that, you know, we're representing fundamentally different physics when we do this. And I started this whole thing by saying that I want to talk to you about porous media and heterogeneous porous media in particular. So far, all I've presented to you was something that is kind of an interesting academic exercise, but not necessarily relevant to that. So I want to take you to some experiments that were conducted several years ago at MIT by Caroline Gramling. And this is one of these really interesting papers where if you look at its citation history, during the first year or two, it didn't really do much. And then a couple of people latched onto this, and it exploded in the last 3 or 4 years, just in terms of the number of citations that are out there. And it's an experiment where initially you have a column that's filled with EDTA, and you displace it with copper sulfate and form a product copper EDTA. The reason the authors use this particular reaction is it's a colorimetric reaction, right? So they can actually relate the concentration of the product, you know, they're using some pretty sophisticated imaging and cameras. They can relate that and calculate the concentration field in space. So this is at an early time, and you have a displacement taking place at multiple different times, and you can see this region here, this is the reactant that is being created. And I'll explain, I'll highlight some of the features of the results here for a second, but one of the things that's happened, and I want to point out, is that a lot of people, right, from this anomalous transport community, that community that I told you about, that they all fight and argue, they've all started throwing all their models at this too, right, and arguing just as vehemently here. And really, this is one, I love those models. I work a lot with those models. This is an application where I think they don't belong. And I'll try to convince and explain to you why. Right? So if you look at, and let me start by saying, again, this porous medium that Caroline Gramling was using was as homogeneous as you could imagine. Right? So you don't expect anomalous transport features to arise or exist, the kind of heterogeneities that I talked about before. Okay, so the nice thing about this chemical reaction, right, is it's really, really, really fast. In fact, it's so fast that you can treat it as instantaneous, right, typically speaking. The nice thing about having an instantaneous chemical reaction is we can actually solve, right, theoretically, we can predict what the concentration of reactants should be under those conditions. And here you have a spatial, so here you have the product against space at a specific time. And this dashed black line here, that is the predicted value of product concentration. The red dots here are the measured values, right? At some later time, you can see that as well. Here you have the total mass of product against time, and the black line here, that is the theoretical prediction, and the dots, the black dots here, are what was actually measured and observed. And there's a few interesting features that I'd like to point out. First and foremost, you always overpredict, right? If you use classical, the theory, you always overpredict the peak concentration that exists, right? It's hard to see on this figure. I promise you in a couple of figures, I'll show you something that makes more sense. You also misrepresent the tails, right? So if you look closely here, what you find is that the red dots are always larger than what is predicted by the theory, right? So you underpredict the peaks and you overpredict the peaks and you underpredict the tails, right? And that happens time and time again. If you look at the total amount of mass that you predict, you tend to overpredict the total amount of mass that is produced in your system. Now, I mean, if you look at this, if anybody who works in earth sciences would look at this and say something like, oh, come on, that's 0.35, that's 0.5. By earth sciences standards, that's an excellent prediction, right? This is not classic earth sciences. This is the simplest column that you can possibly imagine. If you cannot predict this, you can't predict anything in a real aquifer, right? That's kind of the reasoning or the argument in this particular case. And as I say, the second people see things like heavy tails, they want to throw all these anomalous transport models at them. But there's a problem with that. There's another experiment that was conducted in this paper, right, that seems to often be overlooked. And it's a case where there was no reactions whatsoever. So they took the exact same column, and they just do a classic column experiment. And they do this to fit advection and dispersion terms, right, so to measure those within the system. And if you look here, right, you can see that you have the red dots and the blackened. For the most part, the advection dispersion equation seems to do really well at matching it here, right? So a transport here seems to be perfectly represented by advection dispersion, which means that these anomalous transport models that people typically talk about don't belong here. I don't believe that reactions, I personally don't believe that reactions can induce anomalous transport, right? That's a separate debate, but in this particular case, I don't think that's what should be going on. Now, if you look carefully, right, at the data that came out of the experiments, what you start seeing is this. The concentrations, right, the reactants that are being produced, they're not nice, smooth, and clean. They're not these kind of beautiful little mathematical functions that we can describe. There's fluctuations and noise in what's measured as well that look an awful lot like the islands from the numerical methods that I just showed you, right? And so Gramling, she actually said this in her original paper, right? But the idea is that incomplete mixing, right? Incomplete mixing is the thing that is causing these mismatches to take place. So let me just conceptually walk you through here, right? So here we apply the same model, so the same particle-based model that we did before, and you can think about it as follows, right? You set up an initial condition where you have all A on one side, all B on another side. You let the particles jump by diffusion, right? And so now you have a region where you have overlap between red and blue. Okay? Under these circumstances, you expect all red and blue particles that are in this overlapping region to react with one another. But if you go through our algorithm, which is probabilistic, right? So you have to go through and you calculate the probabilities of reaction and interaction between the two, you get this, right? So I go through that reactive process, and you can see some of the blue particles and some of the red particles have been removed in this interaction zone. And that's great, right? And you do this as long as you want. You march it out to sufficient time, and in principle, we should be able to compare this now to Gramling's experiments. Right? If you're interested in the details, again, I'm happy to do that with you. And this is what we get. When we run our particle tracking method, this is what we get. Right? So the red dots, again, is concentration, space, at 3 different times. Red dots are Gramling's experiments. The blue are predictions with our numerical model. And I would argue that we're doing really well. Okay? So we're representing the features that we want to represent. The peak concentrations that we are predicting are close to the peak concentrations that are there. For context, right, for any of you who are looking at this saying it's still not perfect, just for context, this is the comparison. Right? This is what classical theory says. I believe we're doing significantly better than that. And we know why, right? So we have an explanation why, and we'll get to that in a sec. If you remember, I told you that the tails were another region which caused problems. So if you take that same data and you plot it on a semi-log plot, right, now you can see the feature I was telling you. So remember again, the black line, right, this is the theoretical classical prediction. The red dots are Gramling's prediction. So here you can see the classic theory over-predicts the concentration relative to what's measured. But when you go into the tail regions, you measure concentrations that are larger than the classic theory predicts, right? Whereas our model seems to be able to capture that trend much better, right? And this, I wish this was my line, because I love this line so much, but it was Dave Benson who came up with it. In our model, particles can advance further into enemy territory before reacting, right? Because of the probabilistic nature of what's going on, particles here can basically, this guy here has no right to live there by classical theory. But because of the stochastic nature of the world, he can survive, right, and can get through there. And that manifests as these tails in those regions there. Okay, so again, this experiment is the most homogeneous, nice column you could possibly imagine. I started this talk by telling you guys I'm interested in complexity and heterogeneous media. So I'm going to wrap up with that. Right? Again, take you back. This is the exact same experiments that I showed you before. Right? So you have, you're displacing or injecting rhodamine in here. You have this finger region. So what have we learned here, right? From the two examples that I've built up. So starting from the very, very homogeneous nice case, going to the column experiment and going here. Why is this applicable to heterogeneity? Well, in my mind, the reason this is applicable to heterogeneity is if you look carefully at this concentration field, you can see precisely that heterogeneity, what it seems to do is be creating these kind of islands, right? Creating these interfaces that are reacting with one another. If you recall again, I started the talk by talking about the fact that I was interested in mixing, so I'm interested in these green regions, which are the interaction between that red water and the clean water that's there. Unlike a homogeneous medium, right? So this is the homogeneous case where you have a displacement and a nice dispersive region. You have a very, very well-defined dispersion region, right, which has a characteristic scale or size. Here you can see that there's no single size that represents the mixing regions there. You have different structures, different complexities, everything else that's going on. But we just wanted to know, is there anything we can say about these in any reasonable way, right? So to do that, we then went, now we go to hardcore numerical methods, right? So we're not doing this experimentally, but we go to numerical methods because this allows us to explore a large amount of parameter space really quickly. And what we do is we create these artificial aquifers, right? So porous media that have this heterogeneity that spans, I mean, the permeability fields span 10 orders of magnitude. You have velocity fields that looks like this, right? So you have these red, very fast channels and slow trapping regions within there. And this is a snapshot of a concentration field that exists. And the question we ask, right, is the following, is, okay, you can see, right, this guy here is different from this guy here, is different from this guy here, but can we define a characteristic mixing scale, right? One representative mixing scale in these complex systems. And so what you do is you go in, and all of these methods are solved again using these particle tracking methods. What you can do is you can go in and you have your particle distributions, right? And you're asking yourself is, up to what scale are things well mixed, right? And so if a system was well mixed, I should be able to pick any particle, right? Draw a circle around it. Count the number of particles inside that circle. Now I double the size of that circle, right? And if the system is well mixed, I should have 4 times as many particles in there because it should be exactly proportional to the area of the circle that I'm drawing. So I can do this for every single one of my particles. I draw circles of different radii. I count the number of particles that are in there. And eventually, there's going to be a scale at which this no longer holds, right? I increase the size of my circles, but I've no longer got the right number of particles in there. So that's the largest scale over which I can assume things to be well mixed, okay? And if I do that for the simulations that I'm talking about here, I can quantify this. C here means is a correlation function, but I can quantify it this way. So this is a correlation function against distance. This is our different times in our numerical simulations. When this is flat, right, that means that the system is well mixed. And you can see this has this breakpoint here again. Beyond this, right, so at a scale larger than what I'm calling here 10 to the minus 1, the system is no longer well mixed. So as time increases, my region of well mixedness is becoming bigger and bigger and bigger and bigger, which you expect. That's what diffusion does, right? So that's kind of reassuring. Okay, so I have a scale, right? I have a scale to represent mixing, which I'm going to argue is going to be representative of this kind of mixing scale here. I have a scale that represents spreading, right? So this scale here. We know a lot about spreading scales, right? So again, take a step back. If you go back to the homogeneous case, which is advection diffusion, the spreading scale and the mixing scale are the exact same. They're the one and the same, right? Here, they're clearly different, okay? So let's go back to the homogeneous case. Well, we know, right, in the homogeneous scale, the case that this spreading scale, you can show that that spreading scale squared scales linearly in time, right? That's just standard diffusion processes. In heterogeneous porous media, you tend to get super diffusion, right? And when you get super diffusion, what you're saying is that this spreading scale squared scales like t to the power of beta, where beta is a number that is bigger than 1, right? So it's spreading faster than linear in time. And this is really well established. All of those theories that I told you about before, the continuous time random walks, fractional dispersion equations, they can all demonstrate that really, really well. So now you go to the mixing scale, right? And so the mixing scale, we know in a homogeneous system that the mixing scale and the spreading scale are one and the same, which means I know how the mixing scales for a homogeneous system. How about a heterogeneous system? Can we relate the two? Like, is there something? Can I say that, oh, because the spreading scale is super diffusive, therefore the mixing scale has to be super diffusive too? And so we had no good intuition for this. So again, we did this by brute force. And we measured how these things evolve, right? And again, there's a lot of information on this figure, so I don't want you to get too bogged down with this. But here I've got a spreading scale against time. And if you look here at this later time here, you can see that you get this spreading, right? It goes like t to the power of beta over 2, which is the super diffusive regime I'm talking about. If you look at how the mixing scale evolves, right? That's this green line here. We find that it scales like t to the 1 minus beta over 2, right? So this was a single experiment situation. But if you look at these two, you multiply these two together. You say that the spreading scale multiplied by the mixing scale scales linearly in time. The question then is this always true, right? Was this just a freak accident that happened because of a single simulation that we ran, or is it always true? So we ran hundreds of simulations for lots and lots of different configurations. And here you can see what I've plotted here is the mixing scale multiplied by spreading scale divided by time. Don't worry about these earliest times here. That's a different regime. But if what I am arguing is true, that the mixing scale multiplied by the spreading scale scales linearly in time, these have to fall onto this flat line. And you have some variability around there. But again, if you account for the fact that these are very heterogeneous complex systems, I hope you will agree with me that there is strong evidence to support this, right? Spreading scales multiplied by mixing scales.
So what's the difference between each of the cases, though? You just change the statistical nature of the porous medium.
So what we changed is we changed things like the correlation length of the heterogeneity structure. We changed the variance of the field. So you go from weakly heterogeneous systems to very, very strongly heterogeneous systems. What we did not change is we did not look at any. We assumed one heterogeneity structure, right? But we can get into those details later on, right? So all of this is raw brute force, right? This is all kind of numerical experiments, numerical data. So it's pure empiricism. I don't have any evidence for it. If any of you have a clue how to prove this theoretically, I'd love to. But my physical intuition goes along these lines, right? If you have a homogeneous system, what you have is this. You start with a patch that looks like this. By diffusion, that patch grows. By diffusion, that patch grows. In a heterogeneous system, right now what you have is that same patch is trying to grow by diffusion, right? But because of the background flow, the heterogeneity in the flow, it's also being sheared, right? And so if you think about what's going to happen to this guy here, this is going to start spreading, right? So that gives you that large spreading scale. But by conservation of mass, he's also going to have to tighten up in that direction. So the mixing scale has to become smaller, right? So there has to be a balance between these two. But to date, I have not been able to prove this theoretically. I've only been able to prove it by empirical observation. So that brings me to an end on that. But I want to leave with that message that I believe that spreading and mixing scales have a natural balance that exists, right? The really nice thing about this is the following. We have a lot of theories that help us understand how spreading scales evolve, right? So in principle, if we exploit those theories, and this holds to be true, we now also know how mixing scales must evolve, which is pretty nice. So in conclusion, right, incomplete mixing is something, I mean, this is definitely not, in any way, shape, or form restricted to porous media. There's an abundance of applications. If any of you are interested in playing with the model, so the particle tracking models that I showed you before, you can download a version of that code from my website. Finally, this idea, anomalous spreading and anomalous mixing are tightly coupled and connected with one another. I'd also like to just take the chance. I wish I could talk to you about everything that I do in my lab. I can't, right? But I always feel I love these figures here. But these are some of the I do experiments, not very many, but some. They're very simple, right? More kind of results that we've got. And I want to finish with this, right? So this is something that I've started working at Notre Dame. I've started working a lot with ecologists and biologists and really trying to use these methods to understand things that they are observing in streams, rivers, lakes. I haven't convinced people in atmospheric sciences to do this yet, but I really, really believe that. So if you look at current atmospheric chemistry models, especially in relation to climate change and the likes, a lot of them are using grid cells which are 500 by 500 kilometers in size, right? And they naturally have to assume that everything is well mixed within one of those cells. I think these particle tracking methods are conducive to overcoming some of the issues associated with that. But again, I have yet to find somebody who knows enough about atmospheric chemistry to believe me, and then convince them to work with me on this. And then finally, just a little bit of advertising. We have a facility at Notre Dame called the Linked Environmental Ecosystem Facility, where you can actually go and do some pretty cool experiments. We have some artificial watersheds where we can control everything and anything you'd want. Streams connected to ponds, connected to wetlands. And we're running a whole bunch of experiments there. With that, I'll finish up, and I'd be happy to take any questions.
So thanks so much. Are there any questions from anyone? Brian.
When you did bin counting,
Yes.
I do not know whether this is relevant, but there is a beautiful paper by a fellow called Hamburger from maybe 20, 30 years ago in PRL. So he did a very simple experiment. He has a pure random distribution of particles. And then he does the bin counting. And then he finds out that essentially if you have a volume fraction less than 11%, let's say 10%, then the interparticle distances are fractal. They follow a power law.
That makes sense.
If we have higher densities, then you get into non-anomalous range. I do not know how does this pertain to you.
I don't know how it pertains either. So do you, I don't know if you remember, but can you predict the fractal, like the fractal structure?
Yeah, from bin counting, yes.
Okay.
You do those radii, and you see whether you have linear scaling or sublinear scaling.
No, actually, I think that's really interesting because I'm not 100% certain on the connection right now, right? But that definitely attests to the fact that less than 10%, you can't have perfect mixing as a general rule, right? Mm-hmm. So it's very interesting. I'd love to see that paper if you could share it with me.
I'll be happy to share it with you.
That'd be wonderful. Thank you.
So I have a question to follow up with Boyan's then, in a sense. So in the case where you were seeing this anomalous behavior in that first system where you didn't have any heterogeneity in the system, it was purely homogeneous. So
this is the very first problem?
Yeah, when you were talking about the results in MIT, right? That was a homogeneous system, and you saw something then that, as the anomalous people would get very excited because they saw the fat tails. But how would you? So what? And I think it comes back to Boyan's question. So how would you be able to identify if you were going to see that in a system or not? Is it just to do with the concentration of the materials in it? There's no. What would be the character that you would expect to have incomplete mixing?
Oh, I actually believe it. So the first thing is, I think if you have any system whatsoever, which is reaction dominated versus diffusion. So if you calculate a Damkohler number, right? I believe any system where chemical reactions are happening much, much faster than diffusion can bring them together, you're going to get incomplete mixing. I think that's absolutely universal depending on whatever problem you're interested in studying. So I think the thing you need to calculate is a characteristic Damkohler number. If diffusion is much larger than if the diffusion timescale is really fast compared to the reaction timescale, well then things will always be well mixed. Okay. Yeah.
And so in relation then to the second part of the problem, you were just showing how the impact of having heterogeneity in there would actually promote, just for that reason, would promote the fact that you would have this.
Exactly. So I think heterogeneity enhances that. But again, I think if those things homogenize sufficiently quickly, incomplete mixing is not important. Again, this is, I'm not saying this as an expert, I'm saying this based on observations and intuition. Most natural systems have large incomplete mixing. I mean, as evidence of that, geochemists often talk about scale-dependent chemical reaction rates, right? So they say that as they increase the scale over which they measure things, they observe different chemical reactions. That doesn't really make sense from a thermodynamics perspective, right? The chemical reaction shouldn't be varying with scale. Really what's happening is the amount of mixing that's happening over those scales. And as a result, the inferred or effective reaction rate is what's changing.
I know you said you didn't talk about everything going on in your lab, but have you applied your models to groundwater remediation data? There's all sorts of data out there where people inject things down there and then it doesn't behave as they expected.
So we are working on that. So this grant is actually co-funded with Dave Benson at Colorado School of Mines, and one of his PhD students is looking at remediation data, like very, very good remediation data from a site in Michigan called the Schoolcraft site. And they're trying, and again, the idea there is that what they do is they train the model, so they particle tracking model on column experiments that were conducted in the lab to get reaction rates, do these kind of things, and then they, without any further calibration, know that they apply it to the field scale, and they're able to much better reproduce the things that are actually observed in the remediation site. So I haven't done that, but it is being done by my collaborators right now. But that's what motivates a lot of this. I mean, who was it? It was the National Academy, right? They came out with a study that was 19% of remediation efforts fail right now because we're not representing the subsurface accurately at all, and we're using these kind of homogeneous representations that don't account for that.
So, no more questions. Maybe we can. Thanks. A very interesting talk.
Thank you.
Yeah.